In this video, we're going to learn about the second derivative test, which is the second way that we have to determine where our local maxes and mins are. So let's take a look at an example. Here we have a graph that has a local max at A and a local min at B, right? And so let's talk about it in terms of the first derivative and the second derivative. At A, notice that the tangent line has a slope of 0. It's horizontal, isn't it? So that means the first derivative was 0 at that point, and we called that point a critical point. So A is a critical point. And now we have the second derivative as a tool. So notice what happens here. We have a concave down situation, don't we? And that means the second derivative is negative or less than 0. So if we have a situation where the first derivative is 0 and the second derivative is negative, we can say that we have a local max, okay? And worded another way, if we identified this as a critical point and we find out it's concave down at that critical point, we can say we have a local max. Likewise, if the first derivative is 0, so at B we have a first derivative that's 0, it has a horizontal tangent line, that means the first derivative is 0, and the second derivative is greater than 0, so it's a concave up situation, then we have a local min. Then we can say, oh, we know that's going to be a local min, all right? And so worded another way, if we had a critical point at B, and then we found out that it was concave up at B, we could say, oh, this is a local min. So what this leads us to is what we call the second derivative test. And the second derivative test says, suppose that f prime of c equals 0 and that f prime is continuous over an interval containing c. So we've identified c basically as a critical point. If f double prime of c is greater than 0, and we just said that if f double prime of c is greater than 0, that means that it's concave up, then that means we have a local minimum at c. Similarly, if f double prime of c is less than 0, that means that we have a concave down situation, and that means that f has a local maximum at c. And finally, if f double prime of c is equal to 0, then the test is inconclusive. We can't use it, and then we have to revert back to using the first derivative test. So let's take a look at the problem that we did in the video for the first derivative test. We're going to look at it again and use the second derivative test. And the problem was f of x equals negative x cubed plus 3/2 x squared plus 18x. And we found that we had a local min. We did this with the first derivative test. We found a local min at -2, -22. And then we found we had a local max at 340.5. So I just want to identify those points using the second derivative test. All right. So the second derivative test tells us, okay, first you're going to find the critical points. So we find critical points, remember, by taking the first derivative, finding out where the first derivative is either undefined or 0. And so we took the first derivative and we got -3x squared plus 3/2 times 2x plus 18. We simplify that. We get -3x squared plus 3x plus 18. And there are no places where that is undefined, right? It's just a parabola, and parabolas don't have any holes or anything. So all we need to do is set that equal to 0. We can factor out a -3, and we get x squared minus x minus 6 equals 0. And then we factor that into x minus 3 times x plus 2. And then we set those equal to 0, each of those factors. And we get x equals 3 and x equals -2. And we did that with the first derivative test as well. And if you recall, on the first derivative test, we put those numbers on a number line. So we had -2 and 3, and we tested numbers on these intervals to find out, we tested those in the first derivative to find out if the graph was increasing or decreasing during those intervals. And in that way, we identified the local max and the local min. Now we're going to do this a different way. We're going to do it with the second derivative, and we're going to test the concavity at the actual critical points. So the second derivative, here's our first derivative right here, and we need to find the second derivative. So the second derivative is going to be negative 6x plus 3. And so I can now use that to test the concavity at -2 and at 3. So notice here we're not testing points on those intervals. Instead, we're testing the concavity at those exact points. So I'm going to find f double prime of -2, and I get -6 times -2 plus 3, and that is going to be 12 plus 3, which is 15. So that's a positive number, isn't it? So it's positive at that point, and so it's concave up, right? And so if we have a critical point where it's concave up, that means we have a local min, don't we? So we know we have a local min at -2, and we can find the y value by plugging -2 back into our original equation, and we get -2, -22. So that's our local min. And then we can test the concavity at 3. So we get f double prime of 3, and what we get is -6 times 3 plus 3, which is -18 plus 3, which is -15. So we have a negative concave down situation, right? And so, and I put the 2 plus signs here and the 2 negative signs here because it's the second derivative, so I'm just representing it that way. So we have a concave down situation. We know that if we have a horizontal tangent line, which means critical point at 3, and it's concave down, that means we have a local max. So that agrees with what we found here. And so we have a local max at 3. We find the y value by plugging it into the original function, and so that's our local max. It occurs at 3, and the y value is 40.5. So now we've used both the first derivative test and the second derivative test to do the exact same task, and that is to find the local max and the local min of this function. And some students will ask me which one I want them to use, and really the choice is yours. It depends on your preference.